say that chemistry's my hustle, and your brain is like a muscle. So settle in because it's time to flex. Welcome back to another exciting edition of Gas Chemistry. In this video, we're going to be talking about gas chemistry in the lens of ideal gas law. In the previous video, I talked about combined gas law, and in 12.2c, we're focusing on ideal gas law. As you would guess, different name, different equation. Here's our equation. This looks a little different than the previous equation that we did, which was P1 V1 over T1 equal to P2 V2 over T2. Notice that in the previous equation, we have multiple pressures and multiple temperatures. But in this gas law, we only have one pressure, and we only have one volume, and one temperature. So we're not talking about a change in the circumstances, right? We're not talking about an initial container and we're changing it in some way, like changing its pressure, temperature, volume. Instead, we're just relating all the variables at one moment in time. We also have two more variables. What are these things, N and R? Well, N, I know I've mentioned it, the letter anyway, but it's been a little while. N is actually our unit for moles. When you see N, think moles, or the amount of the substance. And that leaves us with R, which can be kind of the most confusing of the ones. It's not necessarily a variable. I describe R as a constant, as it's just a number that makes this equation work. In other words, PV doesn't equal NT. PV equals NT when you multiply it by this constant R. And so that becomes our equation. PV equals nRT. And sometimes chemists refer to this as PivNert. Kind of a fun way of saying it, PivNert. All right. Take a moment. You can pause the video because I'm not going to pause for you. And I'd like you to rearrange the equation to solve for each one of these things: pressure, R, V, T, N, so forth. So take a moment, pause the video, because I'm going to start working at it. For pressure, you should have gotten nRT over V. For volume, nRT over P. For moles, PV over RT. For T, should get PV over NR. And for R, you should get PV over NT. All right. So just like the last gas law, the way that this is we solve these out is determining what variable we're solving for and solving it first in terms of variables and not numbers. Let's talk about R for a second, that gas constant R. It's called the ideal gas constant, and there's actually one of three that you can use in these problems, and that's because it depends on what pressure unit we're talking about. Okay, so there's three big pressure units that we talk about. There's atmospheres, there's kilopascals, and then there's millimeters of mercury, or there's torr. Kind of a funny story there. When we think about barometers, we think about barometric pressure, we think about weather, and we think about units like millimeters of mercury. Well, Torricelli was a scientist that basically brought us the barometer, and that's why sometimes you hear the two units used interchangeably. Millimeters of mercury and torr are equal to each other, so they both work for this. So, depending on the pressure that comes up in the problem, or the pressure that you're solving for, we use different R values. Here are the R values that you'll want to write down, depending on the pressure. If the pressure is in atmospheres, the R value is 0.0821. this R value does have a unit. We could actually solve for it. Remember that R equals PV over NT? Well, if pressure is atmospheres, and volume is liters, N is moles, and temperature is Kelvin, that becomes our unit for this R value. There we go. How about if it's kilopascals? Well, now the value changes. It's 8.314. And instead of atmosphere liter over Kelvin mole, it becomes kilopascals times liters over mole times Kelvin. And if it's either torricelli or millimeters of mercury, the value is 62.4. I'm just going to go with the millimeters of mercury option on this one. Over mole times Kelvin, like that. Okay, so keep that in mind that R has got to be in there, and it just depends on the pressure. Let's do a couple example ones. This is going to end up being a shorter video than the previous video that I put out there. So it says, in our first example, what is the pressure in atmospheres? Okay, so now we know that we're trying to solve for pressure. Exerted by 0.500 moles, well, that's our first indication that we're using the ideal gas law, because the combined gas law does not incorporate moles. This is our N. Of a sample of nitrogen gas, okay, so it says nitrogen gas, but that's not going to change anything. We have a volume, 10.0 liters, at 298 Kelvin. Just like before, we got to make sure that our temperature is in Kelvin, because notice that our R value only works in Kelvin. Okay, let's start with our equation. PV equals nRT. We're solving for pressure. Pressure equals nRT over V. There's really no need to memorize these equations. If you know PV equals nRT, you can solve for whatever one you need. And since we have the units that we need, let's just plug in our values. Starting with N, I would like you to show units. 0.500 moles. For R value, well, what pressure are we solving for? Right? Because there's three different R values. Are we solving for atmospheres, kilopascals, or one of these two? It says in the problem right here, in atmospheres. Therefore, we have to use the one for atmospheres, which is 0.0821 liter atmospheres over moles times Kelvin. Multiply that by our temperature, 298 Kelvin, all divided by our volume, in which is 10.0 liters. Remember how with the combined gas law we can use different values for, or different units for our volume? That's not the case with this one. We need it to be liters because our R value has liters in it. So if you showed your work, then you can do this. You can start canceling units. Liters cancel, Kelvin cancels, moles cancel, and we're left with atmospheres. Let me plug this in quick. And with 3 sig figs, I get an answer of 1.22 atmospheres. Next problem. What is the volume in liters, so we know we're solving for volume, of 8 grams, whoa, what's going on there? I'll just put a question mark, let you think about it for a second. At 20 degrees Celsius, there's our temperature, and 721 millimeters mercury, that's our pressure. Okay, well, let's just get our equation started. We have our PV equals nRT, good old Pivnert, and we're solving for V, so isolating V, we get nRT over P. Now, before we can plug some numbers in here, we really have to do a little bit more work. First, because our temperature is in Celsius, what would this be in Kelvin? If you're adding 273, you're on the right track. It's 293 Kelvin. But what about this 8 grams here? 8 grams of oxygen. That isn't temperature, pressure, volume, or moles. but we can convert this to moles. We did this. Remember back in like unit, I don't know, 2 or 3? If we have 8 grams of oxygen, which is O2, we can convert to moles by using our periodic table. I hope everybody still got one. If you don't, I did post a digital periodic table and equation sheet on Google Classroom under the materials section. For every 1 mole, we add up the mass of 2 oxygens, that is 32.00. So doing a little bit of math, 8 divided by 32 is 0.25 moles of oxygen. So plug it back into the equation. Let's hope that our units cancel. We have 0.25 moles. We have our R value. Well, we have options. Which R value are we going to use? It depends on our pressure. And in this one, our pressure was millimeters. So let's use the one that's got millimeters in it. This one up here. So it's 62.4 millimeters. I'm going to have to make this a little smaller. Let's see. Millimeters times liters over Kelvin times moles. Now let's multiply that by our 293 Kelvin. Divide this all by our volume, or our pressure, which is 721 millimeters of mercury. And because I showed all my work, I can double check. My millimeters of mercury cancel, my moles cancel, my Kelvin cancels, and I'm left with liters. Our final answer on this one will be in units of liters. Let's see. And that gives me an answer of, with 3 sig figs, 6.34 liters. Great. All right, last practice one that we're going to do together. And I encourage you to pause it and try it yourself and then check in. What mass of chlorine gas? Notice they didn't give us the formula for chlorine gas. Let's write that ourselves. Is it Cl? No, because of Brinkelhoff, the 7 elements that are actually molecules in their natural state is Cl2. It's in a 10-liter tank. That's our volume. At a temperature and a pressure. Hopefully you're noticing these things quicker now. That temperature is not going to do. We need that to be in Kelvin. 273 plus 27. I think that's going to be 300 Kelvin there. All right. And we have an equation. Pivnert. In this one, it's asking for what mass? Where do you think we're going with this? Think about that. Where does mass show up in this equation? It actually doesn't. But remember that one of these variables can be converted to mass pretty easily, and that variable is moles. So we're going to solve for moles. N equals PV over RT. And now let's just start plugging things in. We got our 355 kilopascals. Start thinking about R while I'm filling this in here. 10 liters divided by R, we'll come back to that, times our temperature, 300 Kelvin. Well, you got some options, right? It's going to be one of 3 R values. What R value in this one? Since we have kilopascals here, we're going to use the one for kilopascals up here. And that's 8.314. That's kilopascals times liters over Kelvin times moles. All right. Canceling some units now. Kilopascals cancel, liters cancel, Kelvin cancels. I'm left with moles, and you might be thinking, wait, that's in the denominator. You're correct, but it's in the denominator of the denominator. A little fun math rule there. That's going to give us a unit of moles. 355, doing some math now. And with 3 sig figs, why 3? Because 1, 2, 3, 1, 2, 3 for 27.0. We get an answer of 1.42 moles. Ooh, I almost ended this one too early. I forgot what we were looking for. We got our moles, but that's not exactly what we're looking for. We're looking for a mass. Well, that's moles of Cl2. We can convert to mass pretty easily. Just gotta use our molar masses from our periodic tables again. Moles on bottom, grams on top, and the molar mass of chlorine is 35.45 if memory serves. Doubling that would be 70.90 grams. Multiply that by our moles that we solved, and I get an answer of, with 3 sig figs, 101 grams of Cl2. Cool. All right, just like Monday, Tuesday, there will be a form that comes out so that you guys can practice this a little bit more. In addition, you should try pages 8 and 9. I will provide a key for those so you can see how you're doing. Hope you guys have a great rest of your week.